Hi and good day. I am Yong from Group 6 of SEAA3022 IDP1 Section 2. In IDP1, my major presentation will be on Earthwork, and our work is under the guidance of Associate Professor Dr. Mushairry. To start with, I would like to introduce our company Building Your Future. Our company was founded in 2021 and specialized in various fields regarding civil engineering, such as design and build, project management, supervision, quality assurance, and also the consulting services. As a multidisciplinary consultancy firm, we also provide consultancy services on geotechnical field, infrastructure works including roads, buildings, water distribution system, and sewage treatment plants. We aim to deliver the projects efficiently and cost-effectively to ensure the priority of the clients beside maintaining human health, safety, and standard of living. For the major presentation on Earthwork, I would like to separate it into 4 parts, from the project description, introduction and job scope of Earthwork, followed by the project stages of Earthwork, and lastly the slope stability. Now I will start with part 1 about the project. In IDP1, we are asked to in charge of the development of industrial area in Ulu Tilang, Johor. Type of industry that will be built in the proposed area are mostly industry ringan and industry perkhidmatan. There are also some other facilities in the proposed development plan, such as hostel of the workers, water tank, retention pond, and other facilities. The main objective of this development of industrial area is to provide more job opportunities to the nearby residents. Next, we have come to part 2, and I will mainly talk about what is actually earthwork and what actually earthwork covers. Generally, earthwork will be carried out at the early stage of construction. Earthwork will be started with site clearance, followed by excavation, transportation, compaction, and finally disposal. It is important to plan the earthwork properly to achieve the desired outcome with the most effective cost. The first step is the site clearance, which involves the clearing, grubbing, and grading. After site clearance, we then start excavate the earth material until we achieve the proposed level. The earth material excavated is then transported to the field area and compact. After completion of earthwork, the excess material will then be transported out from the site for disposal. In our project, we are required to complete site inventory and analysis. We also need to decide on the proposed level for the area, compute the cut and fill volumes for the project, and also conduct a slope stability analysis. Site inventory and analysis basically involve the gathering and categorizing the data and information for the existing condition. To determine the proposed level, we need to consider the topography and facilities that will be built on it. After that, we will compute the cut and fill volume based on the proposed level, and finally conduct an analysis of cut slope to ensure its stability and safety. In third part, stages of earthwork will be discussed one by one. The first stage of earthwork will be site inventory. We carry out site inventory to determine the existing level for the project site. We have found out that the highest existing level is 88.99 meter and lowest is 31.17 meter. From the site inventory, we can also roughly know the area of the site is approximately 49 hectares and the existing land use is plantation. For the facilities nearby, we have residential area, plaza store, water tank, highway, drainage, and so on. This figure have clearly shown that the location of highest and lowest existing level and also the area of the project site. From Google Earth, we can identify the features and facilities near the project area. There are residential areas such as flat, water tank, bus stop, bridge, highway, plaza to Ulu Tiram, drainage, and also nautical training and consultancy near the project area. After we have done the site inventory, site analysis is conducted. From site analysis, the drainage and water distribution system will be designed based on gravity flow. Hence, the water tank should be located at higher reduced level to facilitate the gravity flow. For the retention pond, it will be constructed at a lower reduced level to achieve a higher water storage. For other facilities and industry, the difference of the reduced level for neighboring area should be concerned. If the difference is big, we need to conduct slope analysis to ensure its stability and safety. After conducting the site inventory and analysis, we start to decide the proposed level. The proposed level is set by considering the existing topography of the site area, including the existing facilities such as the existing road. For the area connected with the existing road, we set the proposed level to be the same as existing road outside to connect both areas. For other area, we determine the proposed level for each zone by taking the average of the highest and lowest reduced level for that zone so that we can minimize the difference between cut and fill. By balancing the cut and fill volume, the overall project cost could be reduced as we are not required to import the soil material or transport out the extra materials. However, we have also considered the future facilities that will be built on the zone because some facilities such as the water tank need to be located on a higher reduced level so that it's able to distribute the water through the gravity flow. The figure in the slide shows the proposed level for each zone. After deciding the proposed level, we start to compute the cut and fill volume. We use the Civil 3D application to compute the volume, and there are several steps need to be done. First, we create the existing surface from the point with elevation provided by surveyor. Next, we create the proposed level surface by drawing the 3D polyline with different elevations for buildings and roads. There are some precaution steps that need to be taken while creating the surfaces. For instance, when we create the existing level surface, points given by the surveyor are not adequate to cover all the area within the boundary. Hence, we need to interpret and add some point to ensure the surface fully covers the area. Boundaries should also be set to ensure the surface only covers the desired area. After two surfaces have been created, we compare the base surface, the existing level surface, with the comparison surface, the proposed level surface, to get the cut and fill volume. These two figures are the surfaces that we create using Civil 3D. The darker the color, the higher the elevation. Cut and fill volume is obtained by comparing these two surfaces. We decide to use the software Civil 3D in computing the cut and fill due to several reasons. First, the manual calculation and computation process using either the manual grid method or cross-section method is quite tedious and prone to errors due to human mistake. The results of the software calculation are also more accurate than those of manual calculation. Any correction or amendment can be easily done by simply adjusting the elevation for the proposed level as what we required. Although we use Civil 3D to compute the cut and fill volume, we also compute it in two different methods, which are grid method and thin method. When we compute the cut and fill volume in Civil 3D, we can choose the method we want to use and compare the result. For grid method, we choose to use a 10 × 10 meter grid. Grid surface is composed of the elevation point on a regular grid. Grid method is smoother and provide a more natural appearance of the derived terrain surface. It's easy to store and manipulate the data since they are in orderly arrangement. However, it also has disadvantages such as not able to cover the whole area due to the limitation on the grid spacing. The boundary area may not be covered when we use grid method. The second method that we use is thin method. Thin is the abbreviation for triangular irregular network. This surface is composed of non-overlapping triangles where each triangle represents one face of the surface. Thin method can reflect exactly the terrain surface based on the elevation information, but it also has its disadvantages, such as the system might connect the elevation of two different features to form a slope, as triangles are generated based on the nearest elevation node. This type of mistake required the proper visual inspection and manual control of the network. This slide shows the result of cut and fill volume. We use 1.1 as fill factor because the fill is compacted to a higher density than the in situ. We also consider the losses in transport, wind and erosion, and also factor of safety. We get the net volume for both grid and thin method. Grid method gives a net volume of 12,600. meter cubed, while team method give a net volume of 35,148 meter cubed. For grid method, we have a percentage difference of 1.32%, while for team method, it recorded a percentage difference of 3.48. Both methods recorded a percentage difference of less than 15% for cut and fill volume, and the result can be considered as acceptable. This slide shows the cut and fill area by using both methods. The cut area is indicated in red color, while the fill area is in blue color. After we have computed the cut and fill volume, we then continue to produce a cross-sectional views. By using Civil 3D and the surfaces created before this, we can easily generate the cross-sectional views. First of all, we create one alignment by drawing one line across the area and create the profile view using the alignment. We then create sample line at the desired station along the alignment, and section view could be produced based on the sample line. All the display styles such as the cut and fill area hedge, elevation range, and so on could be adjusted based on the requirement. We have produced one long sectional view DD and three cross-sectional views AA, BB, and CC at upper, middle, and lower part of the area respectively. This is the long section view DD. The red color H represents the cut area, while the green color is the fill area. The blue line is the final proposed level. The highest elevation is approximately 69 meter and will be cut to 55 meter, and the area will be used for asrama pekerja. The retaining wall will be used at the boundary of the area. This slide shows the cross-section view AA at station 320 meter for the upper part of this project area, and same as previous slide, the red color indicates the cut area while the green indicates the fill area. Retaining wall is also used for both boundaries. This is the cross-section view BB at station 840 meter, which is the middle part of the project area. For this slide, it shows the cross-section view CC at 1360 meter for the bottom part of the project area. For the last part of the earthwork project is to check the slope stability. Slope stability is generally controlled by the nature, distribution, density, and strength of materials that form the slope. When we cut a slope, it will reduce the total stress in the slope and lead to the reduction of pore pressure and hence increase the slope stability in short term. When the pore pressure rises to a new equilibrium value, the materials in the slope may become weak, lead to a reduction of the slope stability. Hence, the slope stability can be said to be governed by the ratio between the available shear strength and the acting shear stress. A slope can be considered as stable if the factor of safety is more than 1. In our project, we set all of our slope gradient as 1 to 2 and use the Bishop simplified method or method of slices to determine the factor of safety. To apply the Bishop simplified method, we first assume the soil properties such as bulk density, cohesion, frictional angle, and also one factor of safety. We then apply method of slice by dividing the soil mass into slices and assume one value of radius. To determine the alpha value, we then draw a line from the origin radius to the center line of each slice. Finally, to determine the factor of safety, we then use the formula to find it. This slide shows the diagram when calculating the factor of safety using the Bishop simplified method. The most critical slope with a difference in reduced level of 10 meter is selected to be analyzed for its stability. We draw a cylindrical surface failure and divide the soil mass into slices. In this method, we need to apply the trial and error method for the value of radius to obtain the final FOS value. For our case, we assume the radius is equal to 15 meter in the first trial and 30 meter for the second trial. This is the calculation for trial 1 and we obtain the FOS is 2.1, which is not same as our assumed FOS 1.7. Hence, the trial 1 is not acceptable and we proceed to trial 2 using the radius of 30 meter. For the second trial using the radius of 30 meter, we obtain the FOS value is 1.7, which is the same as our assumed factor of safety. Since the FOS is greater than the minimum FOS, we can say that our slope is stable. That's all for my major presentation. Thank you for your attention.